we're learning some representation theory, right? So remember that a representation of a group G is simply a homomorphism from G into a general linear group. So in other words, you're picking an invertible linear transformation for each group element so that these transformations have the same relations as satisfy the relations of the group. So this is a homomorphism. And we said that if you choose a basis for V, then you can think of this as choosing a matrix for each element of G. And last time we proved two lemmas. So the first lemma said that if we had a finite group and a representation of it, then we constructed a positive definite bilinear form on V, which was invariant under the action of G. So that was lemma 1. And lemma 2 said the following. It said that any representation of a finite group can be decomposed as a direct sum of irreducible representations. And remember that an irreducible representation, so this representation is irreducible if there are no proper subspaces of V which are invariant under G. That's what it means to be irreducible. And so if you want to think of this lemma 2 in terms of matrices, then what you can think is that you want to choose. So you are able to choose matrices for the elements of G of the form, the following form. So you want to choose a matrix row of G for each group element G. And your choice depends on your choice of basis for V. And so the way you can do this is that you can choose a basis for V. I mean, let's say that rho decomposes as, let's say, rho restricted to V1 plus, etc., plus rho restricted to Vk. Okay, so V is a direct sum of V1 up to Vk, and you can choose basis for V in such a way that you put V1 here, V2 here, Vk here, and your matrices take the form of a bunch of square matrices along the diagonal. And a bunch of zeros outside of these little squares. Okay. So let's prove a couple more facts about representations. So let me make a definition. If you have a group representation from G into GLV, then the centralizer of G is what you know it to be from abstract algebra, basically. It's going to be the things in GLV that commute with all the things in G. So they are the elements of GLV such that they commute with any group element. Now again, I want you to notice that I'm doing something non-trivial notationally here, because what does it mean G times A when G is in G and A is in GLV? Well, really what I mean by this is that G has a representative in GLV. Okay? And so when I write G acting on A, what I mean is rho of G times A. But I want to keep the notation clean, so I do it like this. So this is the centralizer. Okay. So let me observe something, which is that let's say that you have a representation that you have decomposed into irreducible representations so that your matrices look like this. Okay. Now, choose any matrix of this form. So a matrix of the same shape. Okay. And we're going to let each one of these little guys be a multiple of the identity. So this is going to be A times the identity of this size. This is going to be B times the identity of this size. This is going to be C times the identity of this size. In other words, all we have is A is on the diagonal, B is on the diagonal, C is on the diagonal, and everything else is 0. Okay. What happens when you multiply a matrix that looks like this with a matrix that looks like this? Well, remember, because of block multiplication, you can really just multiply this one by this one, this one by this one, and this one by this one, right? But when you multiply a matrix by a constant times the identity, then the identity doesn't do anything, and you're just multiplying the entries of this matrix by that constant. And it doesn't matter if you do that on the left or on the right. So that means that any one of these matrices is going to be in here. Right? Okay, so in particular, the identity, and any multiple of the identity is in here. But what I want to point out is this. If you can prove that the centralizer consists of only the multiples of the identity, I mean, we know that the multiples of the identity are always in the centralizer. I need to make C different from 0 because I need this to be an invertible thing. Okay? If you manage to prove this, then what you have proved is that the block form of this matrix is just, it only has one block. Because if it has several blocks, then there will be more matrices than these guys in here. In other words, if you can prove that the centralizer looks like this, then you have proved that there's only one block, so the representation is irreducible. Okay. So that's one way of proving that a representation is irreducible, is by computing the centralizer and getting this. Okay. So here's another lemma. Let's suppose that you have proved this. Let's say that the centralizer does look like this. Then I'm going to prove the following. I'm going to prove that there is a unique G invariant. Well, let me say unique non-degenerate G invariant bilinear form on V. I meant this to be a V. I realized as I was looking at my notes this morning that half the time I wrote U and half the time I wrote V. So if I'm confusing you with that, then stop me and I'll tell you that I meant V, usually. Okay, so what does this lemma say? Well, first of all, there's a word that I haven't defined for you in this lemma, which is this word non-degenerate. Well, maybe I have defined this, but let's remember what this means. So a bilinear form is non-degenerate if there is nothing that is orthogonal to everything. So there is no V with V comma U equals 0 for all U in V. Okay. So, I mean, you can imagine that the interesting bilinear forms, you don't need this to happen. And so we're saying that this really imposes a very big restriction on what the bilinear forms can be that are G invariant. In fact, there's only one. The only way you can break uniqueness is by doing stupid things like this, but you don't want to do this. Why would you put something be orthogonal to everything? That would mean you're basically disappearing V. You're kind of saying, well, V is basically like a 0. So let's prove this. First of all, how do I prove existence? I need to prove that there is some non-degenerate G invariant form on V. And fortunately, I have lemma 1 here, which tells me just that. I have a G invariant form. Why is it non-degenerate? Because it's positive definite, right? If it's positive definite, that means that V comma V is always positive, which means that V comma V cannot be 0. Okay? So existence is trivial by lemma 1. And so we are going to prove uniqueness. And the way we're going to prove it is we're going to suppose that we have two. Well, suppose these two guys do it. There's such bilinear forms. I realized that I forgot to say something here. Up to scaling. Okay. So in other words, it's unique, except that you might scale it by a factor. So you might say like 2 times this. That's also has this property, but that's the only thing. Okay. So what I'm going to do is suppose that these are two non-degenerate G invariant bilinear forms, and I'm going to show that this one is a multiple of this one. Okay. So I'm going to do it like this. Let U1 up to UN be a basis of V. Okay. Now, when you have a basis and you have a bilinear form, then you also have something called a dual basis. So there is a dual basis V1 up to Vn of V with respect to this bilinear form. And what does this mean? It means it's a basis such that U1 and V1 have inner product 1, and U1 has inner product 0 with everything else. Okay. So in general, the inner product of Ui and Vi is 1, and the inner product of Ui and Vj is 0 for I not equal to j. That's what it means to be a dual basis. Okay. If you've seen this before, then you've seen it before. And if not, you should really do this. It's a nice linear algebra exercise. And I mean, you can do it. It's not hard. But even if you have seen this before, maybe you haven't seen it at this level of generality. And I want you to think about this and think about why, to do this, you need non-degenerate. You need to use the fact that this thing is non-degenerate. Yeah, I mean, basically, if you have something that's orthogonal to everything, then you can't make something like this because you need a basis where no basis element is. You should think about it and see why. Convince yourselves that you need non-degeneracy, but we have it because we're assuming it. Okay. Now, why stop with this inner product? We're going to do the same thing for the other inner product. But then we might get a different dual basis, right? So this is going to have the property, the same property, but now with the bracket inner product. Okay. Now, what's my point? Well, my point is I want to prove that these two guys are actually basically the same thing. They're just off by a constant, by multiplication by a constant. What that probably means is that these guys really are basically the same dual basis, except maybe they're off by a constant. Okay? And so that's what I want to prove. And the way I'm going to prove it is I'm going to just define a function, which I'm going to call phi from v to v by saying that phi of bi is equal to wi. Okay? I can define this because v1 up to vn is a basis of v. And so I just make this, so I define this linearly. So this is a linear function by just defining what it is on the basis. Okay? And of course, what I want to show is that this is just multiplication by a constant, because I want to show that vi and wi are the same thing up to a constant. So this is the phi that I want to explore. Okay? And now, here's what I want you to note is that what happens when you take ui, comma, vj. Well, this is the same thing as with the round bracket. We get the same thing as with this bracket, but with wj here now, which is phi of vj. Okay. Now, this is true for all ui's and for all vj's, and these are linear maps. Okay. So what that means is that it's also true for any combination of ui's and for any combination of vj's. Okay. So by linearity, this is true not just for u and v, but for ui and vj, but for any u and v, because any u can be written as a combination of ui's, v as vj's, and by linearity, I'm going to have this. Okay. Why is that good? Because I'm going to make the following computation. Let's compute this inner product. Okay. You'll see in a second why I want to compute it. So what is this? Well, v is some vector. I apply phi to it, and then I act on it by the group. I'm going to compute this. Well, the thing is the following. First of all, I want to use that this bilinear form is G invariant. So that means that I can act with a group element and stay the same. So let me act by G inverse on the left. Sorry, by G inverse on both sides. I act on G inverse here, I get the same answer. The reason I want to do this is because now this guy looks like something like this. So I can just switch from angle brackets to round brackets and just get rid of the phi. Okay. Now, let me send the G back, okay? Because this form is also G invariant. So I send the G back to the other side. And then you can imagine what I'm going to do is now I'm going to go back to angle brackets. And the way that I go back to angle brackets is by applying phi here. Okay. This is kind of cute because we got almost the same thing, except that G was outside and now it's inside. Okay. Now this is true for This is true for all u, v, and g. Now, if you think about fixing g and v and letting u range, well, here we have found two elements of my vector space, two vectors that have the same inner product with anything. Yeah? This guy with u is equal to this guy with u for any u. In particular, it's true for the basis, and that means that actually these two vectors must be exactly the same vector. It's the only way that a vector can have the same inner product with everything. Let me make this maybe a little bit more explicit than that. I have this, right? And so I can rewrite it as u comma g phi v minus phi g v equals 0. And what did I find? I found something that has inner product 0 with anything. Okay? But because this bracket is non-degenerate, that means that this thing must be equal to 0. So g phi of v is phi g of v. Okay? So what did I just prove? I just proved that g phi is equal to phi g for all g in the group. But what this means is exactly that phi is in my centralizer. Phi is in my centralizer. I did it again. This was supposed to be a v, not a u. Phi is in my centralizer, and my assumption of this lemma is that the centralizer is just a constant. So that means that phi is multiplication by a constant. Okay? Which is what I wanted to show, because this means that wi is c times vi. So really, these two bases, vi and wi, are the same. They're just multiplied by a constant. And that means that these inner products are the same up to a constant. So this is equal to some constant times this. And I guess the constant is 1 over c. Okay. Which is what I wanted to show. These guys really are the same thing. Okay. So that's the proof. Some nice linear algebra right there. Okay. So let's see how we're going to use this. Now, so far, we're talking pretty abstractly about representation theory, and you don't see any Coxeter groups yet on this board. So we're going to fix that now. It's the Coxeter groups class. So lemma 4. Suppose that you have some Coxeter group, some Coxeter system like this. Let's say that it's irreducible. Remember, what irreducible means is that when you draw the Coxeter diagram, it doesn't have separate components. It's connected. Now, with this, we have simple roots. I mean, what we get here, we get a group representation from our Coxeter group to GLV. And this is just the geometric representation, right? The generator, SI, goes to the reflection given by my Cartan matrix. Okay? So I get this group representation on V equals the span of the simple roots. Okay, so this is just the geometric representation. Okay. What I claim is that in this situation, this holds. Okay. Which in particular is going to mean that this representation is irreducible. So how am I going to prove this? Well, I'm just going to consider some element of ZWV, and I'm going to show that it's just a constant. Okay. Okay. So M commutes with all of W. So in particular, M commutes with the simple reflection sigma alpha. So M sigma alpha is equal to sigma alpha M. Now these are, what are these things? Well, sigma alpha is a linear transformation, M is a linear transformation, so these are linear transformations. Okay? And that means that I can plug in any vector into here, and I'm going to get equal things. Okay? So, first of all, let's plug in some vector here that we think is going to behave nicely. Now, the best vector to plug into sigma alpha is alpha. That's the most predictable thing. We know what happens then. Okay. What does sigma alpha do to alpha? Well, it's the reflection that sends alpha to negative alpha. So what we're going to get is minus M alpha equals sigma alpha M alpha. Okay. Now look at what this is saying. This is saying that we have some vector which is called M alpha, whose reflection with respect to alpha is it's negative. But we know exactly which ones are the vectors that sigma alpha sends to their negative. Alpha is one of them. The multiples of alpha are some of them, and they're the only ones. Okay. So that means that M alpha must be a multiple of alpha. It's the only way that sigma alpha is going to send it to its negative. Okay. So M alpha is going to be some multiple of alpha. Okay. And if you look at this, we started with a linear transformation M, and what we just did is that we just found an eigenvector and an eigenvalue, right? And in fact, we didn't just find a single eigenvector and a single eigenvalue, because this is true for any alpha. Right? I mean, I did it for some alpha, but this is true for any alpha. For all alpha for which this is defined, now, in particular, it's true for all the simple roots. Okay? And why do I want to focus on the simple roots? Because I know that V is the span of the simple roots, and what I just showed is that every simple root is an eigenvector. So all simple roots are eigenvectors of M. And that's a step in the right direction, because what I want to prove is that M is just the identity times a constant. Okay? And so what I want to show is that everything is an eigenvector, and that the eigenvalue is always the same. Okay? And so in order to prove that, all I have to prove now is that actually these C alphas are always taking the same value. So that's the next thing I'm going to prove. Now, like I said, I can plug in any vector into here. And so now let me plug a different root. M sigma alpha of beta equals sigma alpha m of beta. Okay? So what does this say? Well, we know what sigma alpha of beta is. We have a formula for that. Beta minus 2 beta comma alpha check alpha. That's the left-hand side. And that's equal to the right-hand side, which is sigma alpha of something. And sigma alpha of something is something minus 2 times inner product of something, comma, alpha check alpha. Okay? And this is good because things cancel out. M beta cancels M beta. 2 cancels 2. So what I get is what? I get M times this thing times alpha. Now this thing is a number, so let me pull it out. So I get this times M alpha equals now M beta comma alpha check alpha. That's what I get. But the nice thing about this is that I know what M alpha is and I know what M beta is, right? Because alpha and beta are eigenvectors. So what I get is beta comma alpha check times M alpha is C alpha alpha. This equals M beta is equal to C beta beta comma alpha check alpha. Okay. Now this is just a number, and this is just a number, and alpha is alpha. So let me forget about that alpha. And so what I get is that beta comma alpha check times C alpha is equal to, let me pull this C beta out of here. So I get this. Okay? And so what this is saying is that either C alpha equals C beta or alpha and beta are perpendicular. Right? For simple roots alpha and beta. Okay. Now, how does this look in the Coxeter diagram? Remember that in the Coxeter diagram, when you don't have an edge, it's because the roots are perpendicular. So if alpha is perpendicular to beta, then what you're going to see in the Coxeter diagram is that alpha and beta are disconnected. And if alpha is not perpendicular to beta, then you're going to see some edge between alpha and beta. Okay. And so what this statement is saying is that whenever you see an edge in the Coxeter diagram, you get that C alpha is equal to C beta. But the thing is that my group is irreducible. That means that my Coxeter diagram is connected. Now, for any two edges, for any two vertices that are directly connected, they have the same C alpha. But this graph is connected, so I just propagate, and I get that along the whole graph, C is the same. So C alpha is the same for all alpha, which means that M alpha is equal to C alpha for simple roots, which means that actually NV is equal to CV for any V in the span of delta. But the span of delta is equal to V. And so what I just showed is that N really is C times the identity, which is what I wanted to show. So that's how Coxeter groups come into this story. And now we're in a very good position because now we have all these lemmas about representation theory that we can apply to our Coxeter group. So let me do that. And let me do that to prove our big theorem that we've been trying to prove for the last few days. What's our big theorem? Our theorem is that W is finite if and only if the corresponding bilinear form is positive definite. And remember that what this means is basically that it's a Euclidean bilinear form. And so we're finally ready to prove this statement that I've been saying for months, that finite groups are exactly the ones that you can realize in a Euclidean space. Proof. So one direction we did already, right? So we already proved that if something is positive definite, then by this compactness argument we found that the group was finite. We did this 2 classes ago. We need the other direction now. So if my group is finite, then we can realize it Euclideanly through a positive definite form. So let's do this. Now, it's a pretty easy exercise to see that if you can prove this for W irreducible, then a standard argument shows that you have it for any W. So it's enough to show it for W irreducible. And then the general case follows easily from that. And now we're just going to basically quote all these lemmas and be done with it. So W is irreducible. And that means that the centralizer is just the multiples of the identity, the non-zero multiples of the identity. So let's see where that's a hypothesis here. Here. Well, here. If the centralizer looks like this, then the representation is irreducible. So the geometric representation is irreducible. So we've used this. We've used this. And you can see we're probably going to use this because this is exactly the hypothesis that we have. Okay. There's a unique, non-degenerate, G-invariant bilinear form on V up to scaling. Now, the thing is that we have this bilinear form, and my point is I want to prove that it's this one. Okay. So I have my bilinear form. Defined by alpha I, alpha j equals minus cosine of pi over mij. And what I would like to show is that this bilinear form satisfies the properties of being non-degenerate and G invariant. So, first of all, why G invariant? Well, remember, what does G invariant mean? It means that the inner product of U and V is not changed if you act by the group. For all U, V, and V, and G in W. But we've been using this fact for months now. So we proved this already, that the geometric representation has this property. So we know this. Okay. Now we would like to prove that this thing is non-degenerate. Okay. In other words, I want to prove that there's not anything that is orthogonal to everything, according to this bilinear form. Now let me do this in a nice way. So here's a slick argument for this. We know that V is invariant under W because it's the whole space. Right? So of course, if you act on something in the whole space by a group element, you're going to land in the whole space because it is the whole space. So V is W invariant. Now, if you remind yourselves of what we did last time, we showed that if a subspace is W invariant, then its orthogonal complement is also W invariant. We showed this. And the thing is, this representation is irreducible. And so it doesn't have W invariant things, except for the only W invariant subspaces are 0 and the whole space. So if this thing is W invariant, then it either has to be 0 or the whole space. Okay? Now, you can imagine that the orthogonal complement of the whole space is not going to be the whole space. Why? Because if it was the whole space, then everything in this space would be orthogonal to everything, and the bilinear form would just be 0 everywhere, which it isn't because these numbers are not 0. So that means that this can't be. Okay? Which means that V perp is 0. And that sounds like maybe it was obvious because V is the whole space, and so V perp should be 0. Well, you see, this is exactly equivalent to being non-degenerate because V perp consists of the things that are perpendicular to everything. And we're saying there aren't any. And that's exactly what it means to be non-degenerate. So this thing is non-degenerate. Okay? In other words, we have in our hands this bilinear form, which is the unique non-degenerate G invariant bilinear form on V. So this is the form that Lemma 3 talks about. Okay. But now, look at Lemma 1. Lemma 1 is telling us about the existence of some other thing, some other form, which maybe I should change the name so you don't confuse it with that one over there. Lemma 1 is telling me that there exists some other form, which is G invariant and positive definite. And we said if you're positive definite, you're non-degenerate. Okay. So in other words, this form that lemma 1 constructs also is the unique thing of lemma 3. So the bilinear form of lemma 1 must also be this unique guy. And now I can put my little square here. Why? Because if this is the unique thing and this is the unique thing, then they must be the same thing. This one, I don't know if it's positive definite, but this one, by definition, is positive definite. End of proof. So I don't know. I mean, it looks like we didn't do anything here. It just kind of magically fell into place. But the thing is, I mean, the way this really happens when you try to prove something like this is you start and you see that every one of these steps takes some work, and then you go and invent representation theory so that you can make these statements, and then you kind of organize it nicely. I mean, the thing is that these are kind of standard representation theory facts that you might use elsewhere, so it's good to have them. But really the point is that we already did all the hard work in the last 2 classes, and now it just all falls into place and proves our theorem. Okay. And so this is our big theorem, finally. It's true. Okay. So now, you saw the proof of this theorem. So this is really the heaviest technical thing that we will do in this class. We really had to develop some topologies, some representation theory. We got here. Now, the good news, if you got a little bit lost with this topology or with this representation theory, is that now it's time for you to start over, because we're not going to use the topology or the representation theory anymore. Now that we have this great theorem, we're going to, I mean, the feel of what we're doing is going to be very different now, because remember, the goal that we have is to classify the finite Coxeter groups. Okay? But now we have this theorem that tells us that what we have to do is classify the positive definite bilinear forms that arise in this game. So we'll do it in this way. And if you look at this, this is linear algebra. It's linear algebra because I'm telling you basically, I mean, it's linear algebra and some combinatorics, because we're going to be playing with this Coxeter graph that gives us this. But really the question is a pure linear algebra question. I give you a vector space, I give you a basis in terms of alpha i's, and I give you this bilinear form. I tell you the inner product of alpha I and alpha j is this thing. And then I ask you, is this bilinear form positive definite? It's a linear algebra question. And what we'll do is just answer it. So we'll see what are the mij's such that this bilinear form is positive definite. So that's the next step. Right. Don't be misled by a statement that I made when I said that to do this you invent representation how it happened historically. Presentation theory was not invented for the purpose of Coxeter books only. Yep.
Yeah.
When did I take the project due?
Friday?
What Friday?
Friday after class is 7.
2 weeks from today.
You got some work to do.
When is the algebra class?
It's on May
First.
yeah, 10:45.
You guys should come to the seminars today. Both speakers are great, and I think the topic will be very interesting.
What are the topics?
Powers.
Actually, the first one you should really come to. It's about like the relationship between combinatorics and statistical physics and this cross-lining physics that you can use.
Wait, cross-lining physics?
Both talks are gonna, the cross-lining is gonna be in there. The first one is, the second one is, rather, Lauren Williams is kind of giving a big overview of a bunch of things from scratch, so that should be. The other one is more algebraic, so it's about half algebra.
Yeah. These towers of things.
Are you going to go get some coffee? Okay, I'll be right back.
Yeah, probably on the
There's a good side and a good day side.
actually, it's on the polygon. And he wrote back saying, because I told my intuition.
We saw that our algebra class has been moved to.
Yeah.
What word was it?
Yeah. It's my intuition. Sorry. It's proving a little bit more formidable. My conjecture is that the polygons greater than 5 can't be realized. Doing that just in a master product. It's just proving to be. I remember talking with you about, yeah, man, why don't you go ahead and like tag that first? Like a short proven shield. It's more complicated many lemmas. So what?
That's good.
Anyway, back to
Cool, cool. I mean, one thing is, it doesn't sound like for looking at the paper, it doesn't sound like this question occurred to them. And I don't want you to be like intimidated by the fact that you just know the answer. You just think about it.
Oh yeah, no.
This is